there. Now I'm starting the recording. So we're starting off with an announcement with respect to office hours. Nikki, do you want to explain?
Yes, so they are replacing windows in this building, and my office, they officially started. So I'm going to be hosting my office hours in the EPLS lab, which is on the 4th floor of North Lindquist. Basically take the elevator and go to the left.
So 494 on the north side is the new location for Nikki's office hours, starting today, 2 to 3:30, and lasting until whenever construction is done. If they told you a month, I would plan on just living there for the rest of the semester. Yeah. I have never seen a construction project actually get finished early in any setting of any kind on Earth. We had our kitchen remodeled when we lived in Lawrence, and it was supposed to take 6 weeks. It took 6 months. So,
Is that why you moved?
It is not why I moved, but it was rough because I was pregnant at the time. And I was like, my baby's not gonna have a kitchen. And that was actually more effective in getting them to finish it than if I had started yelling. Like a crying pregnant woman is like kryptonite for those people. We're sorry. They sent me flowers in the hospital too.
Really?
Yeah, they did. They felt really bad that my baby was not going to have a kitchen. But, lo and behold, I was the kitchen. He was fine. So I didn't have a kitchen. But anywho, beside the point for story time here. Okay, while I have the webpage open, which for those of you just joining us, we're highlighting Nikki's office hours have moved into 494 from where they were before, but also on Zoom, so you can find her in multiple ways. I updated the printable version of the syllabus this morning because I started working on your next homework 2, and realized that since we're a day back in terms of classes, that needed to be pushed back too. So that one won't be due until Wednesday the 27th, which is 2 days later than the syllabus had said originally, which is why I updated it. It's not done yet, so you don't have that to do. So that's not on your list yet. What is on your list, though, is the next formative assessment, which is under quizzes in ICON. So we will take a look at those on Tuesday next week, so please try to finish that by Monday. If you get it done by Monday, you get your 2 points. If you forget and need to do it later, you still get 1 point for doing it. So don't put those off because that's free points in terms of contributing to your grade. Speaking of grades, I downloaded the Homework 1 database and updated grades this morning. So when you log into the online homework system portal, you should see your current point totals. And when you go to your assignment, if you submitted it, you will be able to see all of your feedback. Things that are right will be in green, things that are wrong will be in red, followed by what it should have been in green. If you're looking at it and it's not obvious why you missed something, or you think there might be an error in the answer key, please let me know, and I'm happy to answer individual questions about that. I can't go over it in class because not everyone's done. So that happens. But you can see your own feedback, and you can take a look at things and hopefully work backwards to solve what you would have missed. And the other thing I did, I sent out an email, is I can never leave well enough alone. That's my, my pro and my con simultaneously. So I'll credit Vladimir with this because he was building pictures for a project, and I was trying to explain what they would look like, and I was like, what would be easier than talking what they should look like? Showing what they should look like. So I spent a good chunk of yesterday making some new pictures to go with example 3. So I updated that handout, and I also fixed a typo this morning, and the example 3 files zip folder has a new part to the Excel sheet for the calculations, which is how I made all the pictures. And yes, I know R is great at graphics, and State is great at graphics, and SAS is great at graphics, but I wanted to go for transparency in terms of where the numbers came from, how the predicted values were computed, and how that translates into describing the results of the analysis. So I did it in Excel so that everyone could follow. And now it's a template that you can use in your own lives as well. So those are some updates with respect to schedules, due dates, and such. Anything I'm forgetting? Yeah, we're good to go? Cool. All right. Rock and roll. Then what do we have here? We have slide 30 of lecture 3 as where we were leaving off last time, talking about grand mean centering, constant mean centering, contextual effects, between effects, within effects, word salad it can become. So our goal is to get it to be less salad, more like French fries that are good for you. Would that be sweet potato fries? I don't know. Something like that anyway. I like those the best. Go figure. That's because they're healthy. So we have, let me pull this up here, 2 different versions of the same model. These 2 models are equivalent. They differ in terms of how the level 1 effect of our example predictor was specified. So I have in the boxes above each of these fixed effect solutions a reminder of how these variables were constructed. So as we discussed last time, the issue with level 1 predictors is that they're not just level 1 predictors. You may think these are people characteristics, but to the extent that people are not randomly assigned to their clusters, they are most likely, at least in part, cluster characteristics as well. So our task is to make sure that cluster-to-cluster differences in my predictor, that should translate into reduced level 2 intercept variance for my outcome, has a separate effect than person-to-person variation within cluster, that should translate into a reduction in the level 1 residual variance in my outcome instead. So 2 different effects at play here, and there's 2 different ways to make sure that that happens. So we had the most recent version here, constant centering is what I call it. Grand mean centering or constant centering, those are synonyms for all intents and purposes. I say I like constant centering better because it doesn't matter what constant you pick. You can leave it uncentered, you can subtract the grand mean, you can subtract 10, and I had a question over email, why did I pick 10 here? Because it was the mean, or close to the mean. What constant you pick really just affects your interpretation of the intercept in models that only have mean effects like this, and it matters a little more in terms of level 1 predictors that are to be given random slopes, but we're not talking about that just yet. So any constant. So I have my original verbal ability for each person within each cluster minus 10 here, so that the fixed intercept means something. And it's paired with the mean of verbal ability across students from that school. So it's an aggregate across rows of your data set that you would have to build yourself. And I've subtracted 10 from that as well. These numbers don't have to be the same. I think it's convenient if they are. But towards the middle is usually what people choose. And so in this version of the solution, let me make this a multiple choice question here. Level 1 verbal 10, does that have level 1 variance only, level 2 variance only, or both?
Both.
Both. Subtracting 10 does not change the fact that it is a multi-level variable, just like the outcome is. How about level 2? Does this have, I'll make it an easy multiple choice question. The level 2 predictor, does it have only level 1, only level 2, or both?
Only level 2.
Yeah. So if I think about these 2 predictors competing against each other for predicting variance, what does the level 1 predictor have in it that the level 2 predictor does not?
Within variable?
Yeah, the within, the level 1 variance. And so after controlling for the cluster mean of my verbal predictor here, my level 1 predictor becomes the within slope. So 2.4, if I were to put that in English, which is, I think, on the next page? No, I didn't do that time. I think I had it someplace else. But 2.4 is for every unit more verbal ability a student has than other students in their school. So relatively better verbal ability, that student's outcome goes up by 2.4. So it's a level 1 effect. Within effect, it's relative information only that's affecting the relative outcome for that person. Okay, with me so far? All right. Now if I go over here, the level 1 variable that we have is different. This is the cluster mean centering version, or what is more generally I could call variable centering, because the key idea is that we're not just subtracting a constant, we're subtracting a variable. We're subtracting the cluster mean of verbal. So then once we do that, what kind of information is in this level 1 predictor, WC verbal? Level 1 only, level 2 only, or both? Raise it high. Yes. I had a professor once tell me it is better to be wrong than vague. 1.
All right.
Yes.
I'm proud.
That's right. Level 1 is correct. It's only within information. So because we set it up that way ahead of time to only have within information, That is the only possible interpretation of its slope. It's within. 2.4, exact same number. So we get to the same place either way. One is by doing it ourselves and ensuring it's always going to be that way, which is on the right, cluster mean centering. The other is by letting the model control for the collinearity or common variance between these two, rendering the unique effect of my level 1 predictor as the within slope. We end up at the same place either way. Okay, with me so far? So now, this is the counterintuitive part. CM verbal 10, CM verbal 10, same variable. That is the cluster mean of my level 1 predictor centered at 10. It has two different numbers because these are two different pieces of information. On the right is the between effect at level 2. On the left is the contextual effect at level 2. The difference between these numbers is whether or not you have controlled for a student's verbal ability in anticipating what the effect of the cluster is. You have controlled for it on the left-hand side when you're using constant centering because all of the original information about a student's verbal is still in here. You have not controlled for it on the right-hand side when you use cluster mean centering because the variable you've created is only relative to the mean. It doesn't know how much the person actually had. So the between effect is 3.6. I would say for every unit more average verbal in that school, average language performance goes up by 3.6. And if I were to take a student from that school and move them to a different school, and the student brings all their characteristics with them, then the school's impact on that student after they move would only be 1.2. After controlling for the student, the incremental or extra part that the cluster mean contributes is only 1.2. So saying that again, on the left, the contextual effect controls for the effect of the level 1 predictor. On the right, the between effect does not control for the effect of the level 1 predictor. And everything else is equivalent. Same variance components, same predictions, same model fit, same log, -2 log likelihood, same everything. These are equivalent models in this case because all we have is a random intercept. And if you want to get back and forth between these, you can do that. So in the left-hand solution, within 2.4 plus contextual 1.2 gets me my 3.6. 3.6 minus 2.4 gives me my 1.2. So that's a contest 1D function in R to get the difference between slopes or to get slopes added together. That's a LINCOM in Stata. That's an estimate statement in SAS. That is a test statement in SPSS. That's a new plus model constraint in M+. I think I'm out. Did I miss any? Yeah. You can do it in every package. That's the point of the story. You just have to dig into the documentation sometimes because it's not necessarily obvious. But here's the correspondence. And all of my examples have it both ways and everything. So then, given that these two solutions are equivalent in terms of how they represent the prediction of this outcome, which would you pick? Can you think of a reason why you might lean towards one versus the other? No, are you sewing?
Well, I was just, my brain was thinking,
Okay.
if you're looking for the verb, I'm going to say impact, but I know it's the wrong verb, of the context the student's in,
Mm-hmm.
what you're going for.
That would be one
I didn't
reason.
hear the whole question.
My question is, can you think of situations in which you might prefer one over the other?
I'll stick by my answer.
Stick by your answer. If you're interested in the context addition, yeah, I think that's the clearest one. I've had people argue with me about this before. Yes.
Which, I mean, to get the most precise answer, wouldn't we always want to go toward context then? Because that's going to, I mean, if we add that in, that's going to increase precision in the answer, right?
Well, both of these are equally good choices because
Okay.
both of them have accomplished the objective of avoiding a smushed effect. They
Okay.
both allow a different effect at level 2 than at level 1. It's how they get there that differs.
Okay.
The right-hand side does it directly because you carve up the information into level-specific pieces and then you have your within and your between. The left-hand side does it indirectly because to get to the full level 2 effect, it's actually both of these added together. But to Kate's point, and I think where you were going, if you're interested in the idea of like after controlling for the individual, what is the extra layer that the context brings, 1.2 is the direct answer to that question.
Okay.
So in cluster data analysis, I would say that this left-hand side is probably more common because that's usually the way hypotheses are phrased, is what is the extra part of the context. Not as much in longitudinal. So if you have longitudinal data, then it's occasions nested in persons. The contextual effect in that case would be the extra effect of that person after controlling for the occasions score. And that is, to me, not as useful because occasions aren't things. They're not like entities that are walking around that have separate identities the way people do. So, yeah, go ahead. And
Okay, so
yeah,
kind
you're
of-
both in my pointing
No,
line of sight here.
So kind of in that vein then, if we're taking repeated measures within a subject, is that then more like longitudinal?
Yes, longitudinal would be repeated measures or occasions, trials, something that's
Okay.
repeated within a subject.
And so even if I have the subject with me just for 2 weeks, but take like 100+ observations, it's longitudinal, and therefore the context, the adding the context here may not be as beneficial versus just doing it on the way we did on the right.
Yeah, it's harder to make an example with longitudinal data where the contextual effect would be of interest.
Okay,
For longitudinal, 100%, I would go with the right-hand side.
okay,
And in that context, it would be like, what is the effect of being a kid who does this more than other kids? And then what is the effect of doing it more today than you usually do?
gotcha.
Like, those are clear-cut ways of interpreting things that I think map onto longitudinal data much more directly.
Okay,
For cluster data, it tends to be the left-hand side. Another reason why you might do this, what if you have a binary predictor? Could you do that? Could you have a level 1 predictor that's binary, like whether or not something happens to somebody?
Yeah.
Sure you can. You can do anything you want. This is America. But what would a cluster mean-centered binary predictor be?
Something weird.
Yeah, 0. Like, so if you have 0, 1, and let's say that you are doing something like, I don't know, I hate that example, but gender is the classic binary example, and you have like the gender composition of the school would be the level 2 mean. Well, if you have a school that is perfectly balanced with 50-50 for your binary variable, then your new cluster mean centered variable would be negative 0.5 or positive 0.5. That means 0 doesn't mean anything directly, because there is nobody who would have written down 0. So it gets to be weird, I think, in the context of categorical predictors and demi-coded variables, in which case this version on the left avoids that weirdness. But it's not wrong to do it that way. Okay, yeah, and math. If you don't believe me, just watch. Yeah, all right, some pictures. Want to look at some pictures?
yeah,
Yeah, I like pictures better than math any day of the week. So we have, this is from a paper that I wrote in 2019, and the reviewers wanted me to talk more about contextual effects, so I added some stuff to the discussion that I ended up liking, and so I threw it in here. I tell you the stories behind the stories, right? The story that motivated this paper is a whole separate story, but I'm saving that for later in the semester when it's relevant. So this picture is an example of a lack of contextual effects. So I have an original level 1 predictor with some low values, middle values, high values, and then I have lines for different level 2 means of low, medium, and high. And as you can see from the picture, these lines all kind of follow the same slope. There's not much difference once you control for what the actual value is at level 1. There is not much extra impact of the context here. So the contextual effect that generated this picture is 0.2. The between effect is 1.2, and the within effect is 1. So like if I look at this and I'm like, yeah, what's going to happen to my kid if he moves schools? Nothing, really. I mean, everything sort of follows along the same trajectory. That's another reason why the smushed slope is sometimes called the convergence effect. It's because all the lines are sort of converging onto this common slope. So if this is the case, then there's very little room for like misinterpretation, right? For every unit more of this predictor, your y goes up by, 1, and there's a tiny bit extra that would be added from the context. Now, compare that with the picture on the bottom. This is getting tricky because I have a between effect of 0, I have a within effect of 1, and I have a contextual effect of -1. So I've highlighted 2 people here to demonstrate the context effect. So in this group that has a relatively low cluster mean, so that's the squares here, this person is relatively high. So this person's a superstar in a group of people who are not superstars. Trying to be polite, right? Meanwhile, this person over here is with a group of superstars, but they're relatively less super. So they actually have, even though they have the same score, they have a lower expected value because of the cluster they're in. So then the question is, well, does clusters matter? Do clusters matter? Yeah, this would suggest they're bad for you. But not really. Between clusters, there is no impact. So this is where you have to be very careful, particularly when you have signs in opposite directions. Do clusters matter? The answer is no. Okay, the between slope is completely flat here. Clusters that have more of this predictor than other clusters have the exact same expected outcome. But after controlling for the people, what is the extra impact of the cluster? It's negative. So drawing these pictures gets tricky, and interpreting things gets tricky, I would say, particularly when the signs go backwards like this. So that was the point that I was trying to make. All right. What do I want to do this? I want to do this. I want to do this. Okay, I do want to show you, I'm going to skip that for a second, this table. This summarizes why it is that I usually prefer cluster mean centering. Even if you're interested in contextual effects, you can ask for those separately. And I have many versions of this table, but this one I stole from this article here that's on your reading list. So if I do constant centering, that's on the bottom. If I do variable centering, that's on the top. So variable centering would be like cluster mean centering here. In this notation, I had both a clustered example and a longitudinal example. So rather than going with particular letters, I went with W for within and B for between. So if I have a level 1 predictor that's been cluster mean centered, meaning I take the original variable and subtract the cluster mean, if I put that variable in the model, it has a within slope, the end. And what I'm assuming about the corresponding cluster mean slope that's not here yet is that its slope would be 0. That is standard. Whenever you don't put a predictor in a model, you are assuming it would have a 0 slope. That's what omitting it means. The reverse, if I only put in the cluster mean, that's going to be the between slope because that's the only kind of information that it has, and I'm assuming the within slope is 0 if I leave it out. And if I decide to put them both together, their interpretations don't change. Because in cluster mean centering, you set up the level 1 variable ahead of time to only have level 1 within info. That's the only kind of slope it can have. And you cannot screw this up, right? Everything looks very straightforward. Relative to this monstrosity on the bottom. So if I do the cardinal sin of multi-level modeling, I put in my level 1 predictor centered at a constant, sure. And that's all I put in, that's the smushed effect. And rather than saying that I'm assuming the between effect is 0, I'm actually assuming between effect is there, but it's equal to the smushed coefficient that is both within and between at the same time. So this is a misspecification. This is not I'm assuming there's no effect, I'm assuming the effect is the same. If I take out the level 1 predictor, then the situation is exactly as it was with just the cluster mean above because it's the same model, and that switches to between. And if I have both, then the smush slope is now controlled for level 2 variance. It becomes within only. The level 2 between slope is now controlled for the level 2 part that was already in the level 1, and that becomes contextual. And when I say this is easier to screw up, this is what I'm talking about. Because the terms mean something different when they're paired with their other level counterpart than if they're not. And this is just a main effect, by the way. What do you think happens if I start throwing in interaction terms? Yikes is correct. Your next homework will not have any interaction terms. I'm not going to do that to you yet. But This is just a main effect. The story gets just as complicated. Smushed interaction terms have to get unsmushed and so on. So that's down the road. All right. You want to see an example? Why not? Any questions before we switch gears to an example? We're good? Are you feeling okay with this? Maybe like thumbs past 45 degrees? 2 thumbs up. See, I'm not grading you. You don't have to suck up to me. You already have a PhD. No, I like the participation. When I was a postdoc, I was the person sitting there with my hand in the air every 5 minutes. So be that person. All right, I have example 3 here, the most recent version. The example has 2 new pages at the end that otherwise, if you've already downloaded it, you should be able to follow along up to that point. It's the same data set that example 2 used, so we're building off of that to add in student level variables of SES, which is a continuous variable that mysteriously has a mean of 0 and has decimal values in it. I will take simulated using a random normal distribution for 1,000, Alex. And I know, I'm like, yeah, that's not a real variable. I know it's not. And then they threw in a binary variable for white versus non-white. I'm not going to argue that that means anything in terms of research or theory or even political correctness, but I'm working with what I have. So please accept my apologies for having an example that might be a little bit outdated. In the paper that I stole this from, he made a reasonably decent argument as to why this still might be of interest in terms of looking at this sort of binary categorization, but I did want to have an example of a categorical predictor because these things do get a little bit squishy when that happens. So in terms of data manipulation, that's the first step here, is if we're going to have student level variables, we need to build the cluster means that go with them. And that will be something that you get a chance to practice and verify in homework 2 once I get that out to you. And as I said before, I think Stata wins on this. So to make an aggregate across rows of a Stata data set, that's an eGen, which stands for like fancy generate. I don't know what the extensions to generate. Okay. My process is I gen something, and if it doesn't work, I throw an E in front of it, and that usually solves the problem like 97% of the time. So fancy gen is I'd like the mean of math by school. And it makes you a new variable in that same data set that you can name as you wish, and that's it. So one line of code does the building and the merging and everything in one fell swoop. So I did that 3 times. I am building the cluster mean of math, which is the outcome. I'm doing that so that we can look at descriptive statistics and correlations that are going to be level specific. So the extent to which our predictors can capture school mean variance in math is going to be answered by the random intercept in our models, but this is sort of the observed data version of that. Did the same thing for student SES, and I did the same thing for student non-white. So that's going to be, the latter here is going to be a proportion ranging from 0 to 1. That describes the proportion of students who have a 1 value on this binary predictor. CM stands for cluster mean in my notation. And Stata users, I will remind you that things are case sensitive. So if you stick with my practice of capitalizing parts of the variable name to set it off, you need to do so consistently. Otherwise, you can do everything in lowercase like everyone else does in Stata. But I don't like that, and that's why I purposefully capitalize Stata, even though that's not the right spelling, because I'm just trying to like stick it to the man, you know, who won't respect my love of lowercase and uppercase letters. So, because I've had people send me emails, it's like, you know that Stata is not spelled that way. It is now. So there we go. So we got the Stata code to do that, and then I put descriptive statistics and their results in here for us to look at. So I have in the overall data set, so this is not the level 2 data set specifically, this is combined. I have the mean and standard deviation and range for math. I have the same thing for the cluster mean of SES, excuse me. Note that it has a mean very close to 0, and it ranges between -1 to about 0.8. That's not a real variable, I can tell you that. Non-white has a mean of 0.27, so on average, I would say that 27% of the sample is labeled as non-white, and of course the range is 0 to 1. And if I look at the correlations between these things, so this is what I would call a level 2 correlation table. You know how when you write articles and you have your method section and you usually have like a table of descriptive statistics and sometimes a table of correlations that go with them? Guess what? If you have multi-level data, those correlations are smushed. Oops. Yeah, because you have the extent to which more than other people relates to your outcomes, and you have the extent to which more than other clusters relates to things. Those are two different things. And a Pearson correlation between two multi-level variables is going to mostly reflect level 1. So if you really want to show the analog of bivariate description for your sets of variables, this is the way that you can do it most easily. A multivariate model would probably be a better choice in which each of these becomes a random intercept, but that's not what we're doing yet. That'll be later in the semester. So this is the, I would say, the easiest and straightforward way to be able to report such things. So it looks like at the school level, we have a strong relationship between math and SES. We have a negative relationship between math and the proportion of students who are non-white, and we have a negative relationship between the proportion of students who are non-white and SES at the school level. So that means that these two predictors then would have different effects once you put them together to fight against each other in the model than if they were separate. The idea of shared variance still at work here at the same level. At the original level of the variables here, I have original math, SES, and non-white at the student level. So we've got the descriptive statistics for those as well. And based on that, finding this average of about 0.27 for the proportion for this variable, I centered the school mean at 30. So our reference for the non-white binary variable at the school level will be a school with 30% people who are labeled as non-white. Otherwise, since SES already has a mean of 0, I left that alone. So I'm leaving that one uncentered with respect to predictors.
Lisa,
Yeah, go ahead.
could you repeat just that last part one more time?
Sure. So I'm using descriptive statistics here to try to figure out if I need to center predictors so that 0 means something. And at the cluster mean SES, the mean of that is basically 0. So I'm going to leave that uncentered because 0 is already at the average. So average SES in this fake variable, whatever the hell that means. For school mean proportion non-white, the mean is 0.27. So I rounded it to 0.3. So that means that then my intercept, and once I put this predictor in the model, is going to be the expected outcome for a school where 30% of the students are labeled as non-white.
Got it, thank you.
And I don't have to do that. Now, in this variable, for proportion of students that are non-white, is 0 already meaningful? Is 0 within the scale of the variable? Yes, it is. It ranges from 0 to 1. It is a proportion. So is 0 meaningful?
Yeah.
What does it mean?
You don't have non-white students in that school?
That school is entirely white kids.
Yeah.
There are schools like that in the sample. Otherwise, we wouldn't have a mean of 0. And there are schools where all of the children are labeled as non-white. So I could leave this uncentered, but it leads to potential weirdness. Because if I have a school with no students who are non-white, how am I going to show the non-white effect in that school? Exactly. Now the math don't care. It's like, okay, I'll do that for you, because it's pooling across all the schools to estimate that slope. But I don't want to have to write that in my results section. Like hypothetically, for this school that doesn't have any non-white kids, this is the effect of being non-white. I don't want to go there. So I'm centering it so that the capability of showing the student level variance having an effect is possible in that type of reference school. I try to avoid weirdness when I can. Sometimes it's unavoidable though. Okay, so SES, it already has a mean of 0. I'm leaving that alone. The original non-white binary variable, I'm leaving alone. It is the proportion of non-white students that I am centering near its mean at 0.3. Okay, does that help? Okay, one more step in terms of making new variables, something else you'll get to practice. I am making within cluster or within school versions of these so that I can look at their correlations too. So within cluster SES is the original SES minus the original cluster mean. Same thing with non-white. So note that it's not the centered version that goes here, it's the original. Otherwise, you've centered twice. And I'm doing the same for math, even though it's my outcome, so that I can look at it with the rest of the correlations. And filtering my data set to have only students who have all the pieces of information that I want. And here are the descriptive statistics for these variables. Note the means. What does e to the negative 08 mean?
Ooh,
Alex, you tell us.
yes. That decimal point is like 8, there's like 8 zeros in front of that. So this, well, okay, I guess this isn't a significance thing, but it would be significant if it was a p-value.
Yeah, R spits out p-values in scientific notation. So yes, math people, can you correct us? There's like 8 zeros in front of the first number before we hit that. Is that correct? Am I saying that right? Close enough?
Close enough, yeah.
Close enough. What if it were 8e plus 0.08?
You know, 8.
Yeah, then the decimal goes the other way, and it's a big number. So all of these numbers are very close to 0. They have to be. They've all been centered so that 0 means you're at your cluster mean. So these are relative zeros in this case, yes.
I might have missed it, but is there a reason we didn't center math? Because like, or CMath, because like that's at 12, which is 12 more than 0.
Yes, good question. The reason that, so math has a mean of 12, and 0's within the scale, although this looks like a fake variable too. The reason I didn't build a centered version of math is because it's going to be our outcome.
Okay.
And I didn't need it. We never center the outcome.
Okay.
I am going to the trouble to make a cluster mean of the outcome and to make a within cluster version of it just so I can add it to my correlation tables.
Okay.
That's it. Yep, go ahead.
I know that here we don't have missing data,
Right.
but you are computing your means before dropping your missing cases.
Yes, I know.
Oh, okay, so.
Yeah, my bad.
Okay.
Vladimir is right. This should not be the last step. That should be the first step. Because otherwise the cluster means are going to be off balance if people get dropped that contributed to them. Thank you for correcting that.
Okay.
It's literally just this is always at the end of my code, and so that's just where it was. But I will fix it to do this first, because order of operations does matter in real life. In this fake data set, though, it was already complete, so there's not going to make a difference. But thank you. All right, so here's my within correlations, okay? So this is all relative. If I'm a student who has relatively more money than everyone else in my school, I am relatively stronger in math. Only a little bit, though, 0.2. If I am, let's see, there's a negative relationship between being non-white and math, and there's a negative relationship between SES and being non-white, also relatively small. So just look at the size of these things, right? Much bigger relationships at level 2 than you have at level 1. So that's why I feel like it's important, even at the descriptive stage, to keep in mind the fact that these are 2 different levels of analysis and 2 different sources of variability and covariability, as it were. Those of you using SAS, I have an example that builds cluster means and merges them back into the data set. It uses proc means, and it has 2 different steps. First, the output of the school level data, and then the merge back in. Both of those things are accomplished at the same time when you do the Stata code with the eGen here. Likewise, R users, didn't forget about you. I have an R function that I stole from Jonathan again that is called add unit means. He made a function that does exactly what happens in Stata. So I read in example 3 here. This is the call to the function that will do that. So note the same data set is used in 2 different places in this example. What that's going to do is take the data from the original data set and merge that column back in. So I've had folks run into errors using this function if they tried to use two different data sets. I would recommend merging it back to the same spot just to make sure, because that's what you're going to need to do eventually anyway. It wants to know what your level 2 ID is, and R is also case sensitive. So make sure you get the ID capitalized if that's how you did it. Then it wants to know what variables you'd like the mean for. So I have the 3 here, and then the new names in the order in which they go. CM Math, CM SES, and CM Non. So then this function right here builds my 3 new cluster means, merges them back into the current data set. I then did some descriptive statistics in R. I'm not going to show those here because they have the same output as data, but I used the describe function from the psych package, and then I've had to find, this package, H miscellaneous, I guess, maybe. I'm not sure what that stands for. That would give me a correlation table with p-values. It was surprisingly hard to find. Like, come on! I should not have to fight with R to get a correlation table with p-values, but I did. So I won eventually after figuring out that I had to change my data set into a matrix and then ask for it with this extra function. So then we have descriptive statistics. I have my centered new variable, my within centered variables using the usual process of original variable minus the school mean, the filter for complete cases that needs to be moved up, and then descriptive statistics and correlations further within. So I will be asking for you in your next homework to build these variables, and then I'm going to ask for descriptive statistics and correlations on them to make sure you built them correctly. So every little step of this will help building our way to how to do things. Because it is one thing to understand the concepts. It's a whole nother thing to make the software do what you want it to. Am I right?
Mm-hmm.
Yes.
Yes, in the case of the correlations, I saw that you were using for both kind of variables the level 1 sample size. However, at level 2, we know that we will have one value for each student in the same school.
Mm-hmm.
Is that an issue, or we will have the same result using one observation per cluster, for example?
So the same correlations would happen. So yes, like this is from the full data set. The same correlations would happen if you used just a level 2 data set or a level 1 data set, assuming everything is, I want to say that. It should be very close. If it's perfectly balanced, it'll be the same, but it'll be close if it's unbalanced. But the p-values would be wrong. So like you would want to go to the trouble to build a separate level 2 data set that has the sample size of your number of clusters. And then if you want to use p-values, I would go with that. Yeah, because otherwise you don't really have 7,000 clusters.
Exactly.
So it's kind of like cheating.
Great. Thank you.
Yeah, for this I did it that way because in Stata it's sort of a pain to do a level 2 data set. You have to like preserve and then have it and then like save it and then go back. It's a whole thing, and I didn't want to deal with that. So, but yeah, I'm using this just to sort of like look at sort of data description, effect size kinds of things.
Thank you.
Yes, thank you for the clarification. All right. And where we are? Here we are. Okay, empty model. We did this before, so we can review it quickly. I have this here because we're going to use these results to build and look at variance explained and stuff like that. So we're predicting math per person per cluster with an empty model with an intercept here. So we're using Elmer and we're using Stata mixed to do that. This code you've seen before. So the mean of math is 12. Variability across schools is 8. Variability within schools is 39. Stata reports the likelihood ratio test for whether that 8 is different than 0. Yes, indeed. Decidedly so. Interclass correlation of 0.18. So 0.18 is the proportion of variance that is what? Level 2 or level 1? Two. That is due to random intercept or residual.
Random intercept.
Random intercept. Yes, that is due to between or within?
Between.
Between. That is due to schools being different or people being different.
Cool.
Schools being different. Yes, come up with your favorite set of synonyms. When you're writing a paper, do you need to say the same thing 12 ways? No, you do not. But pick the one that's going to make the most sense to your readers and go with it. That's what I would say. Yes, glad homework 1 worked for folks. Yes, I did have some bad distractors in homework 1, right? So I had some logical impossibilities, like level 2 within school and level 1 between school, right? Trying to drill vocabulary. All right, empty models for the predictors, okay? So this is my outcome, math. I want to know the same thing about my predictors. How much of what is supposed to be student SES and student non-Y is actually school variability? This is important because it tells us whether or not we need to worry about smushed effects, right? Remember we talked about this last time? Maybe? Okay, hypothetically, if I have a predictor with an ICC of 1, what kind of predictor is that? Level 2 or level 1?
Level 2.
That's a level 2 predictor. It varies only across clusters. If it's only a level 2 predictor, what kind of slope can it have? Between, within, or both?
Just between.
Yeah, just between. If I have an ICC of 0, then what?
Purely within.
Purely within? It can only have a within slope. Anything between 0 and 1 means I got both. I got to worry about both. So for this point forward, Stata folks, I'm only showing the R output because it's more condensed. But the full Stata output is inside the download packet if you'd like to follow along for what that looks like. There's basically no difference in terms of what comes out of it. So this is the empty model for SES. We have a variance of 0.16 across schools and a variance of 0.44 within schools. That translates into an interclass correlation of 0.27. So 27% of what we thought of as student SES is actually school SES. The average correlation of students from the same school in terms of their SES is 0.27. So that means we definitely need to worry about having a separate effect of school differences in SES on math than within school differences between children on SES, or in SES on math. And is that 0.26 greater than 0? Here's my Renova likelihood ratio test. So 1768 is the test statistic that I would get from comparing the -2 log likelihoods from the model without the random intercept to the model with it. So you did this before as well. So this is exactly the same code and process interpretation. The only difference is that it's focused on the predictor. So this guides us into thinking logically, what can this predictor do? The fact that it's 27% between means it can have a between slope. The remainder, 73, yeah, nailed it. The remaining 73% means that it can have a within slope. Okay, how are we doing? Okay, now I'm about to say something that some of you will be like, oh yeah, and the rest will be like, what the hell is she talking about? If you fall into the latter camp, give me about a month and we'll come back to this. The other predictor is a binary variable. I can't use the models that we've looked at so far for that. The models that we've looked at so far are for conditionally normal variables, variables whose level 1 residual should be normally distributed. Can a binary variable have a normal distribution?
No.
No, never ever possible. Likewise, can a binary variable have a continuously predicted mean?
It depends.
Not originally, right? Like, what is the highest probability you can have?
1.
1. What's the lowest probability you can have? 0. Our models would not put the boundary fences on that. We need a generalized model. So those of you who've heard of logistic regression and logits, some people have, yes, don't even give me that. Yes. I teach a whole class on generalized linear modeling, so several of you have been through that. Hillary's been through that. Let's see, several of you have been through that. This is the multi-level version of that. So we're switching out the syntax. We're using GLMER, which I suspect stands for generalized Elmer, but I'm going to go with Glimmer on that. It looks like Glimmer to me. And Stata likewise is ME Logit or Me Logit. This is mine, not yours. So it looks a little different because we have to add this piece in the R code. So it's telling us that we want to use a Bernoulli residual distribution. Binomial is the more general form. Bernoulli is a special case for just a binary variable. And a logit link that keeps our predicted probabilities within boundaries. Otherwise, the call looks just the same. And no, you're not having to do this on your homework. Just wanted to show you it for the sake of completeness. In Stata, ME logit understands that what you're trying to do is predict a binary outcome using a multi-level model. So you don't have to tell it anything else. All you have to tell it is what variable you want to use, what your nesting variable is, and then it spits out your results. In R, there's a couple extra pieces that you have to do. If you want an intraclass correlation, you can use the same ICC function that I used before. The only catch, as you'll see here in the Stata output, is that you don't have residual variance. In models for binary outcomes in which you use a logit link, the model implied residual variance is always pi squared over 3. That comes from the logistic distribution. It shortcuts to 3.29. So we don't have an estimated residual variance because of that. We treat it as 3.29. So if you take this random intercept value, put it in the ICC formula in the numerator, and then put 3.29 where the residual variance goes, you get your intraclass correlation. And Stata will spit that out for you using that formula too. I checked. And that intraclass correlation is even higher, 0.63. So what does that mean in this context? It's high, you think? Yeah, I think for cluster data that's pretty high. 63% of the variability in this binary variable is at the school level. Now the fact that it's binary, don't let that throw you off. That means that children are not randomly assigned to their schools with respect to this variable. So yeah, 63% definitely means we need to be worried about contextual effects and between effects with this variable. I have, let's see, yeah, Stata does the likelihood ratio test for it in the same way. To do that in R, I had to do a little extra coding because it didn't understand how to do a likelihood ratio test across different packages, Elmer versus Glimmer. So I did it myself by spitting out the results from GLM and then doing the likelihood difference myself here. So that's just a piece of extra code for you to do that. We will have a unit on how to predict binary outcomes, categorical outcomes, and count outcomes using multi-level models. And we'll talk about logits and such in more detail then. I just wanted to sort of plant the seed that everything you've learned about regression models is applicable here still. If you have a not normal outcome, a standard multi-level model is not going to work in the same way that a standard regression is not going to work. All right. So what we've learned so far, all three of our variables, math is the outcome, student SES, and student non-white status have significant level 2 variance. That means we have a multi-level problem here. So model 2, A. Number because it's a new set of models, A because it's the first instance within this. I'm trying to keep it organized. So I'm taking out the level 2 predictors that were in example 2 because we're not going to talk about those today. We have Zoomers reporting video cutting out. I don't know, is it my video or just their video? Zoomers, are we still okay? See, I'm not even at home. The internet here should work. If the school's internet doesn't work, then I don't know what we're going to do. It's good for you. Okay. Yeah, that did happen at KU one day. Somebody was like doing a construction project and severed like one giant cable that fed the entire campus's internet. And the entire campus went down. It's like, oops. So I'm assuming that did not happen, but okay. Zoomers are reporting that they're still hearing me, so that's good. And I'm still recording, so you shall hear me eventually, if not right now. So first thing I'm doing here, I am putting in all by itself so we can see what happens. The cluster mean centered version of student SES. So note the notation here. It goes in the level 1 model because this is a person variable. It's beta 1 because we're following beta 0 and we count in order. SES PC is the level 1 variable per person per cluster minus the level 2 mean across students from that school, which is then a cluster variable. Beta 1c is a placeholder for how each school is eventually going to get its own effective SES. Right now, that is defined by just this fixed effect here. So, long way of saying everybody gets the same. We are assuming a constant effect of SES that operates across all schools equally. That's an empirical question, but that's not this week. Maybe not even next week. We'll see. It might be Thursday. Do you know what the alternative is besides a fixed slope where everybody gets the same? What's random? What do you think random means? It can do what it wants. Not everything at once, but in the same way that we have each school gets their own intercept via this U-term, next week maybe, or the week after, we're going to have a U-term in here too. And that will allow each school to get their own version of how much relatively more SES predicts relatively more math. Coming soon, but not yet. Just the fixed effect for now. So we have then this predictor here contains level 1 info, level 2 info, or both.
Level 2. Level 1 only.
Any votes besides Vladimir? He's picked twice.
Sorry.
It's okay.
Doesn't it have both since it's got a PC and a C?
This has both. Correct. But when I take this part off, if I take the C off, what's left? Then the P, yes, exactly. So this is cluster mean centering. We are taking out cluster mean differences in this variable and leaving only within cluster people variance. That means without even looking at the numbers, what kind of slope is this variable going to have? Within, smush, between, or contextual?
Within.
Within, because I made it that way. So I put it in the model. Here's my new within cluster SES that I made earlier. That corresponds to this idea. What does 0 mean in this variable?
Someone at the average the school says.
Somebody who is at the average of their school. Not 10, not 15, not 0, school's average. What is that? We don't know yet. That's not in the model yet. So this is purely relative information relative to your school mean. Where do you stand? So I put it in the model as a fixed effect here in Stata, back to mixed, back to Elmer in R, throw it in the model right here. Don't forget your plus sign, by the way. I do that at least 3 times when I'm building this. You need the plus, the random, otherwise it yells at you, and the error is something that isn't helpful, of course. I know, like when are the error messages in R helpful? Like normally not much. Okay, so we got our -2 log likelihood. I am highlighting that as a reminder of this is the number you put into the homework system to make sure that you have it right. And yes, you do need at least 2 digits, whatever the homework says it's correcting to. If you don't get enough digits, there's an option at the top of my code to increase the number of digits provided. So you can use that if it's not cooperating for you. So then we get down here to our results. What's my reference point for the intercept now? It's math. Math is 12 when? When what? Yeah, so when this predictor is 0, that still holds. When is this predictor 0? When you're at your cluster average. So somebody whose SES is average with respect to their school. That person's getting a 12.6. What happens if you are relatively well off? Stupid scientific notation. You do better? Yeah, this is math, so more math is better.
Output? What was our outcome variable?
Math, yeah. Math is money. More money is better. Ergo, more math is better by the transitive property of money. So for every unit more SES a student has than their school, that's the reference here. A student has than their school, that student's math goes up by 2. So this is a student predictor and a student outcome. Here is pseudo R-square. Note that I'm using it relative to the empty model in this case, and I built a SAS function that not only does pseudo R-square, but it also does change in pseudo R-square, so that's what this table is from, because it has everything in one spot. So it looks like these are the variance components from the empty model. These are the variance components from the model that we added within cluster SES. And the within, let's see here, this number right here goes with random intercept variance. The minus sign means what? What does the minus sign mean? Have you ever seen a minus in an R-square before? Because R-square is supposed to already be a minus, right? It's the reduction in residual variance or random intercept variance. So if it's a minus, what is it?
Positive.
Yeah, it went up. My intercept variance actually went up. I have more unexplained school variation than I did before. Now, did I do something wrong?
That's a consequence.
It's a consequence of the way it is computed. What I did do is account for about 5% of the level 1 residual variance. So that means in determining what the level 2 random intercept variance, there's less of a correction factor, it actually goes up. So point of the story, anytime that you explain level 1 variance only, level 2 random intercept variance has to go up as a consequence. They're tied together. I have a slide about that. Did I put it in here? Put it in somewhere. Maybe I have a false memory of that too.
You mean the true
Yeah.
random intercept?
Yeah, I put it in
Formula?
there. Maybe it was
I
lecture
think that was
2.
in the previous set of slides.
Okay, it was a different slide deck. I have a slide about that. But what it is the observed level 2 variance minus level 1 residual variance divided by level 1 sample size. If you reduce level 1 residual, there's less to subtract off. That makes the whole thing increase. So we've explained 5% of the reasons why some kids are better at math because they are relatively higher in SES. That reduction increased the random intercept variance. But otherwise, this is exactly what should have happened. If we have a purely within level variable, the only variance it can possibly reduce is level 1. Because level 1 is purely within variance in the outcome. Now, what if we add the cluster mean to that? Model 2b. So I'm taking my same bar over SES cluster mean variable here, and I'm putting it in the level 2 equation for the intercept. That means I'm making it a main effect. And I'm putting the 0 in here to make a point. The point is, I left it uncentered. So my reference point is an SES of 0, whatever the hell that means. So if your predictor in your homework or your lives does not have a meaningful 0, pick a number to put here so that it does. The choice of whether to do variable versus constant centering is not at level 2. At level 2, your only choice is a constant in a 2-level model. So I throw that one in the mix here. I'm leaving in the previous variable. Still using mixed in Stata, still using Elmer, putting the new one in there. Now we have a slightly different interpretation of the intercept. Math is 12 for what kind of person? Has that part changed? Nope. Somebody who's average in SES with respect to their school. But now, what kind of school does that person go to? When is this variable zeroed out? Whispers.
This school has a mean of 5.8 right?
Say it louder.
The school who has a mean of 5.8.
Uh,
I'm forgetting if the center or not.
5.8 is the coefficient, but it is for a school that has a mean of 0. Yeah, where 0 is like the mean of the variable in this fake variable land. So you could kind of say like this is for SES for an average person from an average school. Like we're just sort of centering it at the middle of everything. Now this number here, 2.19, relative to the previous model, suspiciously similar. Coincidence or consequence?
Consequence.
Yeah, why is it the same?
Because that predictor is independent or orthogonal with the other one.
Yeah, these two are uncorrelated. The predictor that we added has only level 2 information. The predictor that we had before has only level 1. They each stay in their lane. So for every unit more SES I have than my friends at school, my math is higher by 2. For every unit more SES my school has than other schools, my school's math goes up by 5.8. So this is the between slope right here. If I look at the change in R square, empty model is the first two. Previous model with the within slope only here. Model adding the between slope. So my increase in pseudo R square, I now have 68% of the variance relative to the empty model and a change of 69% after overcoming the negative. So if you add these things at the same time, you'll get the right answer. If you do it step by step, intercept variance is going to dip back down, but then come back to where it's supposed to be. So in practice, I add these things together because they are like two halves of the story and each stays in its own lane. The pseudo R square for the level 1 variable, 0.05, pretty much the same, wiggled a little bit, as to be expected because we didn't change the within model. We only changed the between model. So the big jump is in level 2 in terms of the variance being reduced. Okay, how are we doing? Now, what if reviewer 2 is like, but you haven't controlled for each student's SES in this model. You've only controlled for their relative SES-ness. And I have a theory that says that's not cool. You should cite my papers. Dear reviewer 2, thank you for the opportunity to clarify our stance on the deleterious or not so deleterious effects of SES. You know, pick your word, right? To address your concern, what have I done?
Linear combinations,
Yeah, what is the reviewer 2 talking about?
contextual effect.
Yeah, after controlling for student SES. If we want to talk about the impact of school SES that way, it's the difference between the two. So 5.8 minus 2.2 gives me, I think I can almost do this in my head, 3.6? Nailed it. Now what if I want a standard error and a p-value for my 3.6? Can I just like add these standard errors together or something? No, you cannot. There's a formula. I'm not going to bother to teach it to you because I'd rather you make Stata do the math for you, or R, or, you know, whatever. So yeah, that's where our friend contest 1D. Minus 1 goes for the within slope. 1 goes for the between. The end result is between minus within. That's what it's doing. And the intercept is not involved. That's why it's 0 here. So these are multipliers of what you want to do to the fixed effects to create the math. And there's my 3.6. So reviewer 2, thank you for the opportunity to clarify our results. As now stated on page 17, the contextual effect of SES after controlling for individual student SES is 3.6, which is still significant to scientific notation of 18 decimal places. Go ahead.
The question, sorry, is about the interpretation of the slope.
Yes.
So you said that the slope between clusters, 5.8 means 1 unit increase in the average of the cluster mean,
Yes,
then the mass increase that.
the clusters math.
But the cluster mass also come back to level 1. It's the constant of the beta 0C, right?
Mhm.
Won't that lead to the increase of the same amount in the mass PC, like per person?
So if all I had in the model were these two things right here, then all my model could do is predict cluster differences in math. Some clusters would be higher, some clusters would be lower, but all kids within the same school would be the same. So those two numbers get us to where the cluster should be. From there, within cluster gets us to where each kid is relative to their cluster.
But if you just look at the the formula,
Mhm.
isn't whatever goes to level 4, level 2 becomes a beta 0C and it becomes go back to the level 1.
Yes, so this part is what I just said, fixed intercept plus the between effect. This is the random effect that doesn't go into predicted values, but you can think of it sort of that way. Beta 0 then gets us to where each school gets their own whatever. From there, the rest of this swoops in to adjust within a cluster for each kid.
Yeah, so, but if the level 2, that beta goes 5, then doesn't matter what the rest of within the mass will go up at 5.
The cluster's mean math will go up by 5 for every unit more SES. But that applies to all the students within the cluster.
Yeah.
And so then like a more fine-grained student-to-student prediction happens after factoring in the within cluster effect. So I think maybe we're talking about the same thing. Maybe. I agree with you, though. How about that? Okay, 1:45. Any last-minute questions before we call it a day? A week, not just a day. I know. I call it a week on Thursday. Fridays are not usually very productive for me. Yes.
With the contextual effect, the fixed slope at level 1 is the same, and the interpretation will be the same.
Yes.
Okay.
Yep, if we swapped out the version of the level 1 variable, then the solution would change, and that's what we get to do next week. All right, then thanks for being here, Zoomers. Thanks for being here, Roomers. I will catch you on the other side. Let me know if you need anything. Work on your second formative assessment, please. And go visit Nikki in her new digs if you need to.
The EPLS lab